All right, cool. So let's get started. So today we're kind of going to just continue our discussion of acids and bases and introduce a special kind of solution here we call a buffer. All right, today is going to be all about buffers. All right, so first of all, what is a buffer? A buffer is a mixture of a weak acid or base and its conjugate, base or acid. All right, so a mixture of conjugate pairs. If you took a weak acid and its conjugate base and mixed them together, that would be a buffer. Or if you took a weak base and a conjugate acid and its conjugate acid and mixed them together, that would be a buffer. All right, and buffers you encounter all the time in chemistry because buffers resist changes in pH. All right, this is kind of the big deal about buffers. We're going to talk a little bit qualitatively about what I mean by this, and then we're going to prove it quantitatively, okay? But the bottom line is a lot of things are incredibly sensitive to pH changes, right? So perfect example are biological systems. Certain cells are kept at a certain pH, and it turns out that for example, your lung cells are kept at a slightly different pH than your blood cells, et cetera, right? And your body really needs to maintain a very strict pH range or everything gets knocked out of whack. All those biochemical reactions that are keeping us running stop working correctly if the pH changes, okay? So why does the body need to worry about pH changes? Well, it turns out that there's a lot of biochemical reactions that either produce hydronium or hydroxide as products. So a perfect example is ATP. We all know ATP, right? The energy currency of the cell, okay? Well, the process of making ATP necessarily generates hydronium ions as well. So as the cell is making ATP, it's creating these acidic hydronium ions, but it can't have that change the overall pH of the cell, so it employs these buffer systems, right? So all of our cells are buffered. They have these mixtures of a weak acid and conjugate base, and those buffers serve to resist changes in pH as these biochemical processes are going on. All right, and we'll prove this mathematically, that a buffer will not lead to as large of a pH as a solution without a buffer. But first, we got to talk about how we calculate our pH of our buffers. All right, so, we're going to need an example compound here. Okay, so what we're going to do is we're going to create a benzoic acid buffer. Where the concentration of that benzoic acid is equal to 0.75 molar. All right, but if it's a buffer, I don't just have that benzoic acid, I also have, what else has to be in there? It's conjugate base, all right? So I'm going to have to create a mixture here of benzoic acid and its conjugate base. To a concentration of 0.50 molar. Cool. All right, so in order to calculate the pH of this buffer, we're actually going to start in a very familiar place, our acid dissociation reaction. All right, so starting out with benzoic acid here. Oh, that's not it, H7. Complete this acid dissociation reaction. All right, what's my other reactant in my acid dissociation reaction? Water. All right, got a weak acid, so we're going to be good and put our equilibrium arrows. I need my conjugate base, so I'm going to look at my acid formula, take away a hydrogen. And I need my conjugate acids, so I'm going to add a proton to my base water and increase its charge. And we get our acid dissociation reaction. Okay. We're going to need our Ka equation. Ka equals that equilibrium expression of products over reactants. All right, and then what do we use to fill in our equilibrium expressions? Our ice tables, yeah, your equilibrium concentrations. All right, and to get those, we need that ice table. Okay, and here's kind of the first bit of deviation that we see from our normal weak acid problems that we've been doing up until this point, is now we're starting out with a mixture of our weak acid, but we also have some conjugate base in our system initially as well. All right, so when I go to fill out this first row here, usually we only worry about the initial amount of acid, my 0.75 molar, but again, now I have some of that conjugate base that's also in my solution. All right, so I'm going to fill that out there. At this point, no reaction has occurred yet. I've just mixed these two together. Okay, the rest of our table we're going to fill out the same way. Our change box, we're going to have this variable x. All right, what should be the sign of x for that first column? Negative, because it's a reactant. And then these two are positive. Okay, so 0.75 minus x, 0.50 plus x, and then just x. 0 plus x is just x in our ice table here. Okay, and we can turn around and we can plug these equilibrium values back into our equilibrium expression. In order to solve, though, we're going to have to look up what? That Ka value. We said this was benzoic acid, so everybody can take a second and take a look. What's up?
So I remember last week you said this was an approximate page, right?
The KAs?
Yeah.
Yeah.
Where would that be? Because I looked at it over the weekend and I only saw the one we got. You got a table on eligibility.
So the introduction page of each module is where all the documents for that module, including the formulas page and everything like that, is located. So at the very top of our acids and bases module. All right, benzoic acid, 6.5 times 10 to the negative 5. All right, that's our Ka value here. So if we plug everything back in, 6.5 times 10 to the negative 5 equals 0.50 plus x times x divided by 0.75 minus x is our equation here. All right. So we actually could solve it just like this, right? Because we learned how to use that solver function on our calculator. Okay, but we're going to go a little bit of a step further here. We talked about this small x approximation. Okay. And remember, this worked because let's look at this equilibrium, this chemical equation here. The Ka value, the 6.5 times 10 to the negative 5, what does that say about this reaction here in terms of which direction is favored, the products or the reactants? The reactants, and we can even say it strongly favors the reactants, all right? Now, what we're doing different from previous is we're now starting out with some of this conjugate base also in our reaction mixture. And what happens according to Le Chatelier's principle? If we take this equilibrium and we increase the amount of product, what does that shift things in favor of? Goes back this direction, right? So our equilibrium is going to lie even more in favor of our reactants. We're going to get even less of our hydronium product than we would without our conjugate base in there because of Le Chatelier's principle. We went in and we increased the concentration of this product here, so that'll help shift things in favor of the other direction. Okay, so the bottom line is our small x approximation is always valid for buffers, because you're starting out with that mixture. All right, so that means if we go in here, take our equation, all right, we can ignore that minus x from the denominator. But we can also ignore that plus x in our numerator because same logic. If x is really tiny, then 0.5 plus x is going to basically be the same thing as just 0.5. All right. So what we're going to do is we're going to take this here and we're going to derive an equation that we're going to get to use for buffers that's going to save us the trouble of having to do these ice tables and all that jazz. All right, so we're going to have this equation for solving for the pH of buffers, but it's going to be specific to buffers here. All right, so what I'm going to do is I'm going to take this equation here, but I'm going to substitute back in these variables, rather these symbolic variables here. This was my Ka. All right, according to my ice table, X is my concentration of hydronium. All right. That 0.5 is just the initial concentration of my conjugate base. Because of my small x approximation, I'm saying that that is the concentration at equilibrium as well, because I get to ignore this here. So I'm going to say concentration of base all right, and our 0.75, that was just our initial concentration of our weak acid. Again, because of that small x approximation, we say that that is also the concentration at equilibrium. All right, and now we're just going to do some algebra here. We're going to take the negative log of both sides of this equation. All right, and in doing so, we're going to use one of these one of these identities for our logarithms. The fact that the log of a times b is the same thing as the log of a plus the log of b. All right, then this equation would simplify to negative log of Ka equals the negative log of the concentration of base over concentration of acid plus the negative log of that hydronium ion concentration. All right, well, one of these we already got a fancy name for. One of these terms up here. pH, absolutely, right? So we see, right here is pH. All right, and what we're also going to do is define the negative log of our Ka value as what we call the pKa. All right, and if I rearrange this by moving this other term over, we get that the pKa plus the log of base divided by acid is equal to the pH of our solution. Okay, so that was a lot of work to get to this point here, but the bottom line is now we've derived this expression that will give us the pH of any buffer solution here. All right, this is what's called the Henderson-Hasselbalch equation. All right, and again, that is that the pH is equal to the pKa plus the log of the concentration of base divided by the concentration of acid. All right, and this we can use to figure out the pH of a buffer solution, but it only works for a buffer. So we're going to put right next to it here so we don't make this mistake, only for buffers. Right? This doesn't work for any willy-nilly solution. This is just if you have a buffer, a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. All right? Then you can use this Henderson-Hasselbalch equation to figure out the pH of that solution. Okay? So given our example here, we did all this work to derive this equation. Let's actually use it. Take a second and tell me what the pH of our buffer solution is, given that Ka value that we looked up, 6.5 times 10 to the negative 5. All right, so let's look carefully here. The pH equals the pKa, so pKa is just the negative log of that Ka value. That's 6.5 times 10 to the negative 5. Okay. So now I need to do the log of the concentration of base divided by concentration of acid. Well, which one of these is my base? The benzoic acid or this thing over here? Its conjugate base, the benzoate ion. The conjugate base, right? So my conjugate base is my base in this equation. My weak acid is my acid. So this will be the log of that 0.5 divided by the acid concentration, 0.75. All right, so we punch that into our calculator. We get our pH equal to 4.01. We're going to leave it with 2 decimal places here. All right, so for our buffer solution, we talked about a buffer being a mixture of a weak acid and its conjugate base, as in this example. Oh, whoops. Or it could be a weak base and its conjugate acid. All right, and we can calculate the pH of a buffer using our Henderson-Hasselbalch equation. Okay, but now let's go back to what we said the whole shtick about a buffer is. The whole point of a buffer, the only reason why you use it, is because it resists changes to pH. Okay, so let's prove that here quantitatively now. All right. So first, let's just think here if we didn't have any sort of a buffer. So we're first going to think without a buffer. Let's say I take my bufferless solution water. What would the pH of pure H2O be? 7. All right, but now we're going to add to this water some strong acid. So we're going to do our water plus 0.05 molar HCl. All right, if I have a solution that is 0.05 molar HCl, this is a strong acid solution. Everybody take a second and tell me what the pH of that solution would be. All right, so remember this one is one of our easier pH problems because HCl is a strong acid. So the concentration of HCl is simply equal to that concentration of hydronium ions. So I can just take my pH formula, negative log of hydronium ion concentration, and I get a pH of 1.30.
So the presence of the water doesn't affect the pH at all?
Well, that's what we create. The water is just always what we create a solution with, right? So if we made a solution that was 0.05 molar, most of it would be those water molecules.
Oh, okay, gotcha.
All right, so we see that we had this significant drop in our pH here, right? Our pH just decreased by negative 5.70 pH units. All right, so let's compare that now to our buffer. All right, so first of all, we just calculated that our buffer all by itself had a pH of 4.01. Okay, and now what we're going to do is we're going to compare this to what happens if we take that buffer and we combine it with HCl so that we have a concentration of 0.05 molar HCl in there as well. All right, what is the pH here? Cool. All right, so we're going to have to do this calculation here. All right, so this is, we're going to calculate the pH of a buffer plus a strong acid. We're going to keep this same buffer solution to make our lives easier here. So we created this benzoic acid buffer with our concentration of benzoic acid at 0.75 molar and our concentration of benzoate at 0.5 molar. All right, plus now this HCl to a concentration of 0.05 molar. All right, we saw that when we added it to water, it dropped 5.7 pH units. Let's see what's going to happen with our buffer solution here. All right, but first we're going to need an acid-base reaction. Because when we put this strong acid into our buffer, it's going to react with those components in our buffer solution. And in fact, it's going to react with one in particular. Let's think, what is hydrochloric acid going to react with? Benzoic acid or its conjugate base? The base, all right? So when we put this into our buffer solution, the HCl is going to start reacting with that benzoate, that C7H5O2 business. All right, and of course our strong acid is going to play the role of the acid. Benzoic acid's conjugate base is going to play the role of the base. So everybody take a second and give me my acid-base reaction that will take place in this buffer. Oh, thank God. Okay. All right, we're going to blow right past that. So what we're going to make a note of here is in our acid-base reaction, that strong acid reacts with the base in our buffer. Okay, so we're going to do our acid-base reaction here. My conjugate base will be that chloride ion. And now I'll get that benzoic acid as a product of this reaction. Okay? Now we're going to use a familiar problem-solving strategy here, but in a little bit different of a context that we've seen it before, and that is our ice table. All right? We use these to solve these equilibrium equations a bunch. In this case, we're just going to use it to keep track of how much reaction occurs. Okay, because importantly, this is not a reaction where I'm worried about my equilibrium here, right? This isn't a Ka equation where it's in equilibrium, and so I got to pay attention and look up an equilibrium constant. First of all, we don't have an equilibrium constant for this reaction here, okay? Secondly, this reaction involves a strong acid, so this reaction will go 100% to completion here. All right, and this is going to be an important principle for reactions involving strong acids and weak acids or bases. And we're just going to keep in mind all strong will react. Which again is just kind of a shorthand of saying this reaction goes 100% to completion here. All right, so we're going to build an ice table just like we always do. We're going to have all of our reactants and products in here. All right, so everybody take a second, see if you can't build an ice table and fill it in given our initial conditions here. All right, so in this reaction, I have my 0.05 molar HCl and my 0.50 molar conjugate base. I don't have any of those chloride ions, but I do start out with an initial concentration of benzoic acid as well. All right, so initially there is already 0.75 molar benzoic acid in this mixture. My change box, always going to be variables. All right, my HCl and that benzoate are my reactants, so that's going to get a negative sign. My chloride and my benzoic acid get that positive sign. All right, so summing up those first two rows for my equilibrium box, 0.05 minus X, 0.5 minus X, X, and 0.75 plus X. All right, so how are we supposed to solve this ice table here? I'm going to go rogue. We're going to make something up here. We're going to put a whole new row here, make an ices table. And this is for our solution of that equilibrium box. All right, so how are we supposed to know what one of these equilibrium boxes is here? Well, if we look back carefully at this acid-base reaction, we said that this reaction will go 100% to completion, right? Because HCl is a strong acid. So all of that strong acid will react. If all of that strong acid reacts, how much am I left with at equilibrium? 0, right? So I know this box here, this 0.05 minus x has to equal 0. And that will help me solve for the value of x. Right? So x is 0.05. And now I can fill in the rest of my solutions here to my equilibrium equations that I have in those equilibrium boxes. All right, so importantly, how did I solve this here? We were able to set this value to 0 because all strong will react. All right, so that means that there's 0.45 molar of my conjugate base. I made 0.5 molar chloride ions, and I have 0.8 molar of that benzoic acid. All right, so step 1, we built our acid-base reaction here. Then we built an ice table. That allowed us to figure out how much of each component was left over. So now let's do our final pH calculation. Okay, so first of all, we got to look at this table carefully here at what we actually have in this mixture after this reaction's taken place. Do we have any hydrochloric acid left over? No, so I don't really care about that in terms of calculating a pH. That's all used up. Okay, I have my conjugate base here and my benzoic acid. And then I also have some of these chloride ions that have been formed when this reaction occurred. All right, now the question is, do I have to worry about those chloride ions when I'm calculating my pH? All right, let's remember, we talked last class about this inverse relationship between the strength of an acid and its conjugate base. If it was a weak acid, then we got to worry about its conjugate base. It's also weak. But if we have a strong acid, what can we say about its conjugate base? It's neutral, which is a fancy way of saying I don't care about it if I'm calculating pH, right? It's not going to contribute to the overall pH of my solution. So I can just ignore because it's neutral. All right, so when we do our pH calculation, we're going to ignore the neutral product. So then if we ignore that neutral product, the only thing I'm left with is benzoic acid and its conjugate base. And we have a fancy name for mixtures of weak acids and their conjugate bases. What is that? A buffer, right? And we have that fancy equation we can use for our buffer solution, our Henderson-Hasselbalch equation. So since what we're left with is a buffer solution, we're going to use Henderson-Hasselbalch. All right, so everybody take a second, see if you can't use our Henderson-Hasselbalch equation. That Ka value again was 6.5 times 10 to the negative 5 for this buffer. And then you'll have to update your concentrations of base and acid. All right, so looking carefully at this ice table, what value am I going to use for my concentration of base? What value? Which number up here? The 0, the 4.45, 0.05, 0.8. Which one's my base concentration? That 0.45. And my acid concentration is my 0.8. I punch all this into my Henderson-Hasselbalch equation, and I get a pH of 3.94, rounded to those 2 decimal places. All right, so let's just go back and update here. With our buffer, our pH, and our HCl, we got now 3.94. Okay, so what happened to our pH? Did it remain perfectly constant? No, it's still decreased. But how much did it decrease by? This is a difference of 0.07 pH units. Compare that to adding that exact same amount of acid to water, where it decreased 5.7 pH units, almost 100 times more of a difference adding that acid to water than to our buffer system, right? So again, buffers will resist changes to pH. They will change pH very much more slowly. Slowly is kind of the wrong word, but anyway, compared to systems that do not have buffers. Okay, so by adding this strong acid, yes, we decrease the pH, but far less than if we had added it to an unbuffered solution like water. All right, that's the whole idea of a buffer. I will say I was a biochemist. Literally every single experiment I ever performed was in a buffer solution. Every 6 months you sit down and you prep like 100 bottles worth of buffer for you to use throughout the next upcoming months. It's a huge part of a lot of lab work, especially things that have like biological implications. Cool. All right, we're going to do one more here from scratch. You guys are going to take this, see what we can do based on what we learned here. All right, so we're going to create an acetic acid buffer where the concentration of that acetic acid is equal to 1.25 molar. And the concentration of that acetate conjugate base is equal to 2.40 molar. All right, so first, let's figure out what is the pH of our buffer. All right, we are allowed to use, because it's a buffer, we can use that Henderson-Hasselbalch equation. We do need the Ka of our buffer system here. So let's look that up for acetic acid. All right, that's that 1.8 times 10 to the negative 5 value. All right, so punch that into my account. Again, the Henderson-Hasselbalch, the pKa is, the pH is equal to the pKa plus the log of base over acid. I gotta put my conjugate base in the numerator, that acid in the denominator, and punch that into my calculator. And I get a pH of 5.03. All right, and now we're going to take that same buffer and we're going to add hydroxide to a concentration equal to 0.50 molar. All right, last time we added a strong acid in there. Now we're going to add this strong base in there and ask what is the pH. All right, and what we need to do is the same steps that we did before. I'm going to give you all a big head start here, and then I'm going to quietly fill in. But we want first the acid-base reaction that's going to take place when that NaOH is added. We're going to keep track of how much reaction occurred using an ice table. And once we have that ice table complete, we can calculate our pH.
How do we know that we're adding NaOH?
I'm saying we're going to add hydroxide here. You're being given that information, right? You're starting out with this buffer here, and you're adding a base to a certain concentration.
Right, where's the sodium?
It could be any counter ion, but importantly, that counter ion isn't really what's playing the role of the base. So whether it was sodium hydroxide, potassium hydroxide, barium hydroxide, what matters is the hydroxide concentration, because your base is hydroxide. So, and I mean, just to sort of note, anytime I see something like NaOH, in my mind, I immediately drop that counter ion and put a negative charge, because that's what's my base in an acid-base reaction. The sodium ion is what we call a spectator ion. It's just kind of floating around, not doing anything.
Okay, thank you.
Yep.
Maybe the question too that I had was, if we were to write an acid-base reaction and we were just given the information there, would we just automatically know it was NaOH to put in?
You're going to use the hydroxide ion when you do your
Oh, okay.
acid-base reaction. You could do NaOH, and then you would have an Na on the other side as well. But I think, you will see that some places, I like to cut the crap here. The Na isn't doing anything. It shouldn't be in that chemical reaction. It's not playing the role of an acid or a base. What's important is the base is that hydroxide ion.
So we could just put OHs.
Yes, yep. Right, so importantly, when I'm adding that hydroxide, it's going to react not with the conjugate base, but with the weak acid, acetic acid. All right, so I got my chemical equation here, my acid-base reaction, where I use that hydroxide base and my weak acid, right? So that's what's going to be playing the role of my acid in my buffer mixture is that acetic acid. This will give me water and my conjugate base of my reaction. Putting those initial conditions into my ice table, I have my initial concentration of my weak acid, my initial concentration of that product, my weak base, and my concentration of hydroxide here. And then I did my variables, my X, where my reactants were negative X and my products were positive X. Okay. Now again, we can fill out one of these. We know one of these equilibrium boxes. We know its solution here based on the fact that we have a strong base in this reaction. And again, we say all that strong reacts. Right? So then if all of that strong hydroxide ion reacts, how much am I left with at the end? None of it. Okay, cool. And this is what allows me to figure out what X is. Right? So now I can say, all right, great. Well, that means 0.50 minus X is equal to 0, or X has to be 0.5. All right, so then plugging that value in here, that means I'm left with 0.75 molar acetic acid. I've created some water. And I now have 2.9 molar of my conjugate base here. All right, so now we're going to go on to calculate our our pH. We don't have any of that strong base left over. Do we have to worry about how much water has formed? No, I mean, arguably including concentration of water was not quite correct anyway because it's a pure liquid. But regardless, I wanted to prove a point here. Again, we have this neutral product, and we don't have to worry about how much neutral product is formed because it's not going to impact our pH here. So we get to ignore that neutral product. And then we're just left with the buffer solution here. So we get to use that Henderson-Hasselbalch equation. Our pH equals that pKa plus the log of our concentration of base over acid. That pKa is what we looked up before, or rather the Ka is what we looked up before, that 1.8 times 10 to the negative 5 plus the log. What's my base here? What value am I going to use for my base? Yeah, my 2.9, my acetate concentration. Divided by that acetic acid concentration of 0.75. All right, punch that into our calculator. We get a pH of 5.33. All right, so just to summarize here, our buffer all by itself had a pH equal to 5.30. Nope, 5.03. Then we took that buffer and we added 0.5 molar hydroxide. That took us to a pH of 5.33. All right, so our pH, it did increase by 0.3. All right, so we added a strong base. We did see an increase in our pH. All right, but if we compare that to water, again, the pH of water would just be 7. Well, if we took that same water and we created a solution with 0.5 molar hydroxide, now all of a sudden our pH would be 13.7. All right, so it would have increased a full 6.70 pH units if we hadn't had our buffer in there. But with our buffer, we just see an increase of 0.3 pH units, right? So again, our buffers are resisting changes in pH when either strong acids or strong bases are being added. We see a much smaller increase in pH in our buffer than we would without a buffer. All right. One more thing to note, because this is kind of a subtle point, and I did gloss over it. A lot of people are like, wait a minute, isn't it sodium hydroxide? Why are we just adding hydroxide? And I get it, because yes, if you go to the store, you don't just buy hydroxide ions, you buy sodium hydroxide. So another way that we could have written this same exact chemical equation here would have been to instead include NaOH. All right, but if you're going to include the sodium on the left-hand side, it's got to be on the right-hand side as well. And so where you would see it paired up with is with that negatively charged conjugate base here. And that's how we could do our balanced chemical equation. Now, I hate this because I think it's super deceiving. All right, as soon as you put sodium hydroxide and make it into an aqueous solution, it is not going to stay sodium hydroxide. It's going to dissociate into sodium ions and hydroxide ions. Right? And same thing with that conjugate base. It's not like they're stuck together in solution. These things are floating around separately as sodium ions and acetate ions. Right? And so this is my kind of preferred way of looking at this would be the net ionic equation where we say, all right, sodium's not doing a dang thing, so I'm going to cross it out on both sides. And this is really my acid-base equation. Okay? So if that was confusing, don't worry about it. We're always just going to use hydroxide as our strong base, but that's the reason why. That's why I don't include the counter ion in there. All right. Lastly, one more thing to note in our sort of list of notes about buffers. All right, we talked about how they are a mixture that resist pH changes, and we can calculate the pH. Importantly, there's also what we call the effective buffer range. All right, we saw those past two buffers. I mean, we proved it using the math that they resisted changes to pH. But they don't do so over the entire pH range, okay? Each buffer has a kind of unique portion of the pH spectrum where it acts as an effective buffer. And that pH is always its pKa plus or minus 1 unit. All right, so a given buffer is only really effective when the pH of the solution is close to that of its pKa, right? Plus or minus 1 pH unit of that pKa. Outside of that, it's not going to effectively resist changes to pH. You're going to see the pH spike if you add a strong base, for example, if it's outside of this range here, okay? So this is our effective buffer range. Buffers are only really good at doing what buffers do, which is resist changes to pH inside that range there. Whoa. Okay, cool. That's it. Sweet. We will meet back for lab at 2:30, normal lab time. Y'all are in luck. It is not the most complicated lab in the entire world. I know people are very disappointed that there's no calculations that are going to be a part of today's lab, but it is a pretty cool lab. It illustrates Le Chatelier's principle pretty well. Oh yeah, well, we'll do all